before I go into finding limits numerically, I did want to point out that we've been doing that. We've been using the idea of limit numerically. For this example, that it's on page 29, the rate of change. If we want to find the average rate of change at 2 seconds, we're trying to find the rate at which this bungee jumper is falling at 2 seconds. What we can do is make these values, these seconds, get really close to 2. So between 2 and 2.5 seconds, he's falling at a rate of 30.75 feet per second. Between 2 and 2.1 seconds, he's falling at that rate. Between 2 and 2.01 seconds, he's falling at that rate. And if we get this distance between these two x coordinates go to 0, if we make that distance approach 0, we're finding the limit of the average rate of change as the distance h approaches 0. And we get not an average rate of change, we get now an instantaneous rate of change. So these two values are so close together. That's exactly what the instantaneous rate of change is. At 2 seconds, the bungee jumper's height is decreasing at a rate of 41 feet per second. So now I'll show you how to set up a table for finding the limit of a function. Here is our function x cubed minus 1 over x minus 1. And if you want to find this limit of this function as x approaches 1 numerically, what you want to do is you want to set up a column, an x column or a row. I'm going to do rows in this case because your lab manual sets it up in rows, but you could do columns if you want. And you would type the function in. So our function is, you need parentheses to group the numerator. Is this cell B1 is our first x value, so x cubed minus 1 close parentheses divided by x minus 1. And again, it thinks that there's a 0 here, so there's no problem. Now what we want to do is approach 1 from the left and the right. You need to check the limit of f of x from the left and the right. So maybe we'll start at 0 and get closer and closer to 1 from the left. And then there's 1. And then we also want to check from the right. So a really close number to 1 from the right is 1.001. And now if we take this cell here that has the function in it and we plug it in, then we are evaluating the function at all these values. And as we go and approach 1 from the left, it goes from 1 to 1.75 to 2.71 to 2.9404 to 2.9701. Now when we evaluate at 1, you see it's got an error because you can't put 1 in the denominator because you get 0 in the denominator. But we're not worried about evaluating. We're trying to find the limit. So this I'm going to just delete. And then if you look at the values as x approaches 1 from the right, you go from 4.75 to 3.64 to 3.31 to 3.03 to 3.003. And so you can see how it's approaching 3 from the left and approaching 3 from the right. So the limit of f of x as x approaches 1 is 3. Over here I have shown you the algebraic way. This x cubed minus 1 actually factors. There's a trick to factoring a difference of 2 cubes. This factors into x minus 1 times x squared plus x plus 1. If you don't know the shortcut for factoring, you could have divided out x minus 1 into x cubed minus 1, and this is the quadratic you'd be left with. You can cancel the x minus 1's. You're left with x squared plus x plus 1. Now you can plug 1 in. 1 plus 1 plus 1 is 3. So this checks out algebraically. And here's the key, and I kind of like this key a little bit better because I got really close to 1 from the left and really close to 1 from the right. And so you can see a little bit better how it is approaching 3 from the left and 3 from the right. And I also did it in columns. So you can use columns or rows. Okay, let's find this limit numerically. So we will set up our column, our rows, and we want to find the limit of this function. I'll put this function in. It is x, which our cell B1 is our x, divided by parentheses square root sqrt of B1 plus 1, close the parentheses for the square root, minus 1, now close the parentheses for the denominator. And right now it thinks you're evaluating at 0, and that's why you get this undefined. We want 0 to be in the middle, the value for x in the middle, and we want to get really close to 0 from the left, so that might be something like negative 0.00001. Okay, and then approach 0 from the right might be something like 0.00001. And we'll continue to evaluate those values. So when we're trying to find the limit, remember we don't care what the value at x is 0 is, it's undefined because you get 0 in the denominator. What we care about is what the function is approaching, is what the function is equal to as x approaches 0, and it looks like 2 on the left, and it looks like it's approaching 2 from the right as well. So the limit of this function as x approaches 0 is 2. Incidentally, trying to find the algebraic limit would be difficult. You would have to multiply by the conjugate of the denominator. You would have to multiply by square root of x plus 1 over square root of x plus 1 plus 1. And then you would be able to evaluate. But this is just finding the limits numerically, so this is just as good a way to find the limit as any other way in this context. Okay, here's our first application problem. It says the following bar graph shows U.S. Math SAT scores as a function of parents' income level. These data can be modeled by S of x equals 535 minus 136 times 0.979 to the x power, where S of x is the average average math SAT score of a student whose parent income is X $1,000 per year. Numerically estimate the limit as x approaches infinity of S of x and interpret the result. So this bar graph is given, but the function is also given. So the bar graph is actually not really needed, although you can see what's happening in general as the income level of parents goes up, the SAT math score is going up. But we want to find the limit of the function of the SAT math score as parent salary in thousands of dollars goes to infinity. So what we would do, the same thing, we're going to have an x and an S of x, and then x stands for salary, income in thousands of dollars per year. So if I let income be 0 and then 10,000 per year and then 100,000 per year, and I want x to go infinity, so then and 1,000,000 per year and then 10,000 thousands per year, that's a big enough salary to estimate infinity, I think. So then I'm going to type in the function, which is 535 minus 136 times 0.979 caret x, which I'm going to click on the cell B1. Now before we find the answer, you actually can do this algebraically using your x approaches infinity rules. See if you can do that. What happens when you have infinity in for x here with 0.979? 0.979, which is less than 1, raised to the infinity power. That's going to go to 0. And then 136 times 0 is 0. And then 535 minus 0 is 535. So let's see what happens. If we find the limit numerically, it seems to be approaching 535. So the way you would interpret this, remember our Math English Dictionary, which I didn't write down. X is income in thousands of dollars per year. S of X is average math SAT score. So as the parent's income gets really large, we don't want to say approaches infinity, we want really good English words. As the income gets really, really large, the average math SAT score of a student is going to approach 535. I like the word approach here because we're not evaluating. It's as it gets really large, it's approaching 535. Okay, here are two more examples. Here's that 0.979 to the x. Again, you could do this algebraically. As x approaches infinity, this is going to go to 0. So this fraction is less than 1, meaning the denominator is going to get bigger than the numerator as x approaches infinity. So that's going to approach 0. And again, 1.5, that's 3 over 2 to the negative x. That's the same thing as 2 over 3 to the x. If you make x approach infinity, that's going to go to 0. But I wanted to show you what this would look like. These infinity ones, you want x to just get bigger and bigger and bigger and bigger and bigger, and you plug the functions in and you can see that they both go to 0 as x gets really, really large. So you can do the infinity limits just numerically, just like any other limit. So on your lab manual, page 25, you have limits numerically. We've got 6 problems for you, but we've already given you the table of x values to use. We won't do that on the test, so the reason we've picked the values we have, remember you want to evaluate the limit as x approaches, in this example, 2 from the left and 2 from the right. Also, you can do several of these algebraically, either by just plugging in, since 2's in the domain, you could plug that in, or by factoring and then canceling. So try those problems. I wanted to do a couple of limit application problems. The first one, there's not much math in terms of the Excel work. It's just a graph, and the following graph represents the monthly price of United Airlines stock P in dollars for the period February 2006 until July 2009. So each of these tick marks is 2 months after February 2006. And you can see that the price is fluctuating, but it's a continuous fluctuation. And then when you get to the 24th month after February 2006, from the left, the stock is about $41. The limit as x approaches, m approaches 24 from the right, means we would look backwards in time. And the limit as x approaches 24 from the right is about $31 or $30. And so since the limits are different from the left and the right, the limit does not exist. So interpreting this limit, there's a variety of ways that you could interpret it. The point is that these limits are different from the left and right, and there's an instantaneous drop in stock price that you could not have predicted. So I just put we could not have predicted the drop in the United Airlines stock in the 24th month after February 2006. So the second one is another piecewise function, and this time you have function equations, so it's a good time to review how to do a piecewise function. But first I'm going to read the problem and define my variables. The concentration in nanograms per milliliter of a 360 milligram dose of a blood pressure medication in a patient's blood during the 24 hours after the drug is administered is described by the function C of H, and then you have the function. The independent variable H is time, and the unit is hours. And the C of H is the concentration in nanograms per milliliter. So the units are nanograms per milliliter. Those are tough units, but if I read the problem and think about it, I can write this down first. Then it helps me when it's time to interpret. We want to find the limit of this function as h approaches 10. So what we want to do is the same thing we usually do with limits, which is 10 is the number we want to approach. Now you can graph this whole thing. In fact, I will. I'll go count by twos and go to a 24-hour period, and then I'll show you what I'm going to do at 10. Okay, so this is the 24-hour period. Remember to do piecewise function. You go up to the fx box, and we're going to find the if function. And then you get these three boxes. And remember, this 0 here is not going to be in our logical test because we can start at 0. It's this h is less than or equal to 10 that we want to put in this first box. So h is represented by the cell A22, and then you have less than, and then you have equal to 10. Now if this is true, then you will put this first equation in, which is negative 0.51 times h caret 3 plus 7.65 times A22 caret 2 plus 125. So I just typed in that first equation using cell references, and looks like I hit that way too soon. Okay, so then the value of faults, that's the second equation, so that's negative 16.07 times A22 plus 540.7. And then we'll drag that down, and I want to graph it. So there is something happening at 10 as we suspected, because the first part we're using this cubic function at 10, and then the second part we're using this line. So remember to do the limit. I just did this just to see what we have here. To do limits, you want to kind of investigate what happens as x gets really, really close to 10 from the left and the right. So I am clicking on these rows here, right-clicking and inserting some rows. And I'm going to get really close to 10. So 9.999, 9.99, 9.9. Maybe I'll insert 9. And I'll just drag down the function. And then close to 10 from the right would be 10.001. Maybe I'll insert. You can insert as much as you want until you feel good about what you're looking at. Okay, now what we don't care about is what this 10 is equal to. We want to know what the limit of the concentration is as we approach 10. And as we approach 10 from the left, it's 380. As we approach 10 from the right, it looks pretty close to 380 as well. I'm going to keep looking, so I'm going to add a, seems like it's approaching 380.2984. Okay, I had to pause the video because I wasn't getting the answer I expected. Technically, this limit does not exist because from the left it's approaching 380 and from the right it's approaching 10. Well, you may have noticed, and probably screaming at the video, I have a typo. When I typed in negative 16.07, I made a mistake and typed in 0.04. So I can go in here and change that. Now I'm going to drag this all the way down there. And now it is legit. I'm approaching 380 nanograms per milliliter as we approach 10 from the left, and I am approaching 380 nanograms per milliliter as I approach 10 from the right. So we have computed the limit if it exists, and it does. And you know, it's 380. That's the numerical value, and I'll go ahead and interpret it here in B. So we want to not use words limit or anything like that when we interpret. So I'm going to look here at this as the number of hours approaches 10 hours. The concentration of medication approaches 380, and then your units, nanograms per milliliter. So we don't use the word limit. We wouldn't use the word infinity if it were an infinity problem. I like to use the word approach though. And so you can see as we get close to 10 hours in the bloodstream, the concentration approaches 380 nanograms per milliliter.